A very warm welcome to this session on the basics and fundamentals of serverless. I'm Srushith Repakula, Head of Engineering at KonfHub. You can find me at on Twitter at the rate SrushithR. So a brief introduction about myself. As I mentioned, I'm the Head of Engineering at KonfHub. I'm also a serverless consultant, co-organizer of one of the largest serverless meetup groups, the Serverless Architecture Meetup Group from Bangalore. And I'm also an organizer of the recently started AWS user group from Tirupati. If you guys are interested into AWS and serverless, you should probably do join these meetup groups for some interesting content from us. And I'm also a mentor at Girls Script Bangalore. So without any further delay, let's get started about the session. So this is the evolution of serverless. So this session is all about the basics and fundamentals of serverless, what it is, and how we reached to the point where we are today, and what are the advantages, disadvantages, if at all there are any, and how it is leveraged by developers, startups, enterprises for various other reasons. So this is a very basic evolution diagram of Simpsons, of course, where the very beginning we had the physical machines, where we had large rooms, server rooms, where there were a lot of server machines, and we as individuals or a particular team used to maintain, manage the same, and then came in the virtualization wherein we had virtualization on the physical layer. That means the physical layer was taken away. And then came in the cloud, where we really did not have to manage anything ourselves. We didn't have to buy infrastructure. We didn't have to maintain them, but leverage what is available in the cloud. And later on came the containers, where there was one more level of abstraction that was possible. I will just give me a second. I'll explain it to you further in detail, whatever these abstraction layers are. And later on came in the serverless, which was another layer of abstraction from containers, which meant that with serverless, all that we worry about or care is just the business logic and nothing else. We don't really care about, or rather maintain, the servers behind the scenes. And of course, if you guys have attended any of the previous serverless sessions, you guys might have already heard this statement a zillion times, that serverless doesn't mean there are no servers, but just that there are the servers, we don't have to manage it ourselves, but rather the responsibility is given to the cloud provider for the maintenance of the servers. So basically, at every individual level of our evolution, we had one abstraction and a few things that have been taken away from us as developers. And the cloud provider, in this case AWS, takes care of everything for us, and we don't really have to worry about the same. So that's pretty much of the evolution. Now, if we get a little in depth of and try to understand what has happened, what are the pros and cons at every individual level, we have the physical machines, which is the very first part of the evolution, where we had big server farms and stuff like that. And as most of you guys know, we call them server huggers. There are a set of people who are called as server huggers, who are very much preferred to have their data in their own data centers on-prem and manage and maintain the same. But with that particular approach, there have been a lot of cons and disadvantages. A few of them have been mentioned here, which is basically, every time you want to scale your application when there's enough load, then new infrastructure has to be provisioned. That means we have to physically go and purchase that infrastructure and add it to the fleet of servers that we already have, and therefore the application will have enough infrastructure to scale when there is more load. So basically, there is a lot of planning that needs to go in when it comes to going the physical machines way for building our applications, that is the on-prem mode. And a lot of planning, as I've mentioned, needs to go in. And all these things lives for years, because we have actually invested our money in purchasing the physical machines. And then apart from that, which means that there's a lot of heavy investments in terms of CapEx planning. And then there's a low innovation factor, because With physical machines, physical servers, we will not have the capability to leverage the various numerous fastly growing services on the cloud. If you guys have followed, there are close to almost 200 services that is available on AWS. And imagine running your applications on-prem using physical servers, then we will not be able to leverage all the capabilities that the cloud brings to us. Then and of course the deployment can range in months. We will not be able to deploy as frequently as we would like to, and therefore the feedback cycles, the innovation factors, everything go down. Then the next layer, as of from an abstraction perspective, is the virtual machines. A lot of customers and enterprises have adopted the virtualization and moved to virtual machines on the cloud because of the various advantages. Like we don't really have to maintain the servers ourselves, but rather it is the responsibility of the cloud provider, that is AWS in this case, to take care of the servers, maintain it in terms of the physical capabilities, like the server rooms, the heating capabilities, the electricity, the failovers, all these things are taken away from us, and we don't have to maintain all those things from that perspective. Therefore, we get hardware independence, and hence we will have a faster provisioning speed. Basically, with physical servers, we are limited to our capability of the physical machines that is available to us, but rather in virtual machines that is in the cloud, we are not necessarily limited by anything, and as much as resources that is available in that particular region or availability zone can be consumed by us on as and when we need. There's a lot of load, we can get in as in uh, how much ever more virtual machines can be spun up. And therefore, it also opens up the capability for experiments. So in the case of physical machines or physical servers, let's say, for example, you want to bring up or try out a particular application, then there's a lot of planning, as I've already mentioned. And for whatever reasons, the particular project has not gone as planned, and we have to kill it. Then we have already put in a lot of investment into procuring the resources. Therefore, it will be a lot more challenging. Whereas in virtual machine world, where you are just relying on the cloud, as and when you want to build a new product, you bring up the resources that is required, and then just basically go ahead with building your application. If it goes well, then you can scale up as and when you, because this is cloud, you don't have to procure any resources yourself, but rather spin up more virtual machines, VMs. Or if it's not functioning fine, you can kill it down, and just we don't really have to worry about it. And one of the other advantages is basically the global deployments that comes into picture, where it's not about deploying it into one particular region, but rather various other global regions that is available as a part of the AWS cloud, and the different AZs, the failover mechanisms, and things like that that can be very much relied on. Apart from that, it also opens up the increased innovation factor, because we can leverage the various services that is available on the AWS cloud. The 200 services that I had mentioned, we can leverage the same. And therefore, we really it also opens up the capability for more scale. We can have some automations wherein we can add more VMs that can be spun up, and of course which helps us in faster speed and agility from a product development perspective and deliverability. Of course, there's reduced maintenance, because we don't really have to worry about maintaining the servers as ourselves. Cost is one of the main reasons why a lot of people are migrating to the virtual machines on the cloud. But a lot of times, the major priority or major reason for people is the innovation and adoption of the latest services that is available on the cloud. After the virtual machines came in, the containerization, wherein it gave us the capability, it provided us high degree of mobility, wherein the application that we are trying to build is becoming is platform independent. Therefore, I build an application and deploy it wherever I want, on-prem, on VMs, on the cloud, everywhere, without really bothering about the platform where I am deploying. Therefore, giving us a great a great opportunity to not rely on the underlying infrastructure as is. and therefore it provides us consistent runtime environment because it has a confined environment where the application is running. And it is easier and faster deployments when compared to the VMs and the physical machines, of course. And it gives us a greater capability in terms of spinning up more containers. Hardly takes a few seconds when it comes to deploying or spinning up new containers, therefore giving us the capability for having a very agnostic and platform independent application. But then even in this particular mode of compute, we still have to maintain the servers and a lot of configuration that needs to go in, and therefore came in the serverless where we are right now, wherein everything is on demand, everything is event driven, which means that there is no infrastructure dedicated just for our application, but rather, as and when there are requests coming in, infrastructure is provided for our application, the code gets deployed into it, and the request is served, and then the infrastructure is no more available. So basically, it's all event driven. Request coming in, infrastructure is provided, the particular purpose is served, and then infrastructure goes away. What is the advantage of this? The very first thing is we don't really have to bother about the underlying infrastructure. There is no configuration that is required from our end. All that we have to bother is write or solve real world problems, build your application, product, add more features, and stuff like that. As developers, what is our primary focus? We really have to be worried about solving real world problems, not really bothered about or concerned about the underlying infrastructure, and worried about whether I have provisioned enough compute capacity so that when there are requests coming in, so that I don't really get conged, right? And there is not a lot of latency for my particular customers. So all these things, all these problems, capex planning, over provisioning or under provisioning, is all taken away from our hands, and the cloud provider AWS takes care of making sure that it scales up and down as and when there are requests coming in. So this is one of the biggest advantage, giving the developers the sole focus to work on to focus on building applications. The other important feature it brings in is the pay as you go, which is basically, in the serverless world, we only pay for how much we consume. It's not like we are provisioning a VM, and irrespective of whether there's request coming in or not, I'll have to pay for the VM on an hourly basis, right? It's not the case here. As and when requests are coming in, only then the infrastructure is provided for us. Therefore, only at that particular moment, AWS charges us for the same, and therefore we are not charged extra where there is no load that is coming for our application, and we are not charged anything. So pay as you go, that is pay for value, is one of the biggest advantages other than the scale and the capability it gives us in terms of infrastructure. And therefore, of course, there's zero maintenance because, of course, we are not really bothered about anything underlying. There's no infrastructure, there's no server maintenance, patching, OS upgradation, security patches, nothing of these sorts, because AWS takes care of the same. From an infrastructure perspective, if you're using different modules and stuff like that, it is still the onus is on us as developers to make sure that the modules are having the corresponding security patches and stuff like that. The other thing is the fault tolerance is built in, which means that for whatever reason, a particular Lambda function, Lambda is basically the serverless service on AWS. For whatever reason, the Lambda function is not working as expected, then what can happen is we don't really have to bother about it. AWS takes care of making sure that another Lambda function is provisioned and the particular request is served. So as we can understand that at every individual layer of there has been a particular abstraction that has happened and made the lives of developers easier, giving us more flexibility and capability to what we want to achieve. Now, these are the various reasons why we have to go serverless. Of course, I have already mentioned a few of them earlier. As we said, no servers. There are no servers to provision or manage for us as developers, and we configuration-less scaling. Now, for you guys to understand, let me just give you a simple example. We have Book My Show, which is a movie ticketing platform, right? And let's say we have built our own movie ticketing platform, and we are selling movie tickets, right? And because of the COVID situation that we have been in for the past few months, we have not got we have got not got an opportunity to go to the theaters in person. Therefore, our application, which is meant only to sell tickets, is actually out of business, right? Because there are no theaters running, and therefore we have no visitors coming to our application to buy tickets for movies, right? So in such scenarios, let's say for example, we take the VM approach where we had an EC2 machine which we have spun up and which takes care of serving the request that is coming in. In such scenarios, we just cannot kill the virtual machine, right? Because we are certain that no visitor is going to come to our website to purchase tickets. But that doesn't mean that I can kill down the server and not have any infrastructure at all. Therefore, I at least have to have one VM up and running all the time. But what is the disadvantage of that? The disadvantage is, even though I know that there is not going to be any request coming in, I have to have an infrastructure up and running, and therefore I have to pay AWS for the same, right? Imagine the same thing now. Let's say, for example, now the theaters have started opening, and we have a few visitors coming in. Now, imagine there is I don't know how many of you have attended my previous sessions. I'm a big Marvel fan, and let's assume that Black Widow is releasing. It was supposed to release before the entire pandemic happened, and imagine we have Black Widow releasing. I don't know how many of you will be willing to go and but I will be most eager to go and watch Black Widow in the theaters, although it is the COVID situation and all those things. Therefore, what would happen is the moment I say, the tickets for Black Widow is open on my platform, there will be a lot of requests coming in, given the scale of Marvel, there will be a lot of requests coming in. Imagine I had one server and then suddenly I open the ticket sales for a particular movie, huge requests coming in, and probably the infrastructure that I have provided, that one VM, may not be sufficient, right? Of course, there's hundreds and hundreds of requests that is coming in, and my infrastructure is not able to provision. So what should I have done? Because I know Black Widow will have a lot of traction for my application, for my ticketing platform, I should have pre-planned and added more servers so that it can add more scale. It can serve more scale. So that planning should have happened. But with serverless, let's assume the same platform is built with serverless. What would have happened is, let's take the first half of it. When there are no requests coming in, we don't have any infrastructure that is available because everything is ephemeral. That means everything is on demand. Therefore, I don't have to pay AWS a single penny. Again, a star mark, of course, assuming that you are only using Lambda functions and everything is serverless. In that case, we really don't have to pay AWS anything, right? Because there are, what is the motto of serverless? I mean, one of the fundamental factors is pay as you go. Nobody's consuming it, so I'm not going to pay AWS anything, right? The same thing with when it comes to scale, when we have a lot of requests that is coming in, I don't have to plan for anything. I know Black Widow will attract a lot of people to my platform, but I don't have to plan for anything because serverless can scale without my intervention, without any configuration. So that is the magic of serverless. It can automatically scale with usage on both ends of the spectrum. That is zero requests. I don't have to pay anything, but my infrastructure is there. I don't have to be scared that, okay, don't have any infrastructure. What will happen if there is a user coming in to just view my website, right? I don't have to be worried about it when there are almost zero requests versus the other end of the spectrum where I have so many requests that is coming in. I still don't have to bother because AWS is going to take care of scaling it up and down as and when there are requests coming in. So built-in tolerance, we have already discussed, pay as you go, we have already discussed, and bring in your own code. So this is one more thing that we have not I did not discuss on the previous screen, which is basically, excuse me, which is basically whenever we are moving, one of the challenges for people who are migrating to the cloud and then are looking at various options like containers and serverless. They have this perception that moving to serverless means re-architecting, yes, to a certain extent, and redesigning their entire application. It doesn't really have to be the case. Of course, we will have to change our thought process when we are building serverless. That is basically, as I've mentioned, it's all going to be event driven, and we have to think in that perspective and build our application. And from a coding perspective, a lot of changes need not happen when you're migrating into serverless. Minor tweaks, understanding of how the Lambda environment works, which I will be discussing in some time, will actually help you migrate to serverless, and you can leverage all the other advantages that I've been talking about, especially the pay as you go. One of the biggest things that people see in serverless is the pay as you go and the automatic scaling. Now, coming to how does Lambda functions work or working with serverless, right? We have a bunch of event sources that is available. We have the serverless functions, that is our Lambda function, which we are going to pay by usage. And then we have other services. Now, as I've already been mentioning, working with serverless or Lambda functions means it is going to be event driven. That is, as and when there is a request that is coming in, the compute happens, your code is executed, and the request is served. So let's take a simple example here. We have our application wherein we are converting images from PNG to JPG. So what will happen is I have an application where my end users can come in, upload their PNG images, and then it will get converted to JPG images. One of the best examples of serverless applications. Here what happens is the event source is nothing but an upload of an image to my S3 bucket, right? So what will happen is when a user comes to my website, uploads an image, it's basically an upload to an S3 bucket, and that is a trigger to a Lambda function. As and when there's an upload, that upload will trigger a Lambda function automatically. We don't have to do anything. And that Lambda function will have your business logic of converting that PNG image to JPG image, and then probably uploading the converted JPG image to another S3 bucket, right? So like that, we have numerous event sources that is available on AWS. A few of them are changes in a database. For example, we have DynamoDB, our NoSQL database. We have DynamoDB streams, and we can have DynamoDB triggers. So whenever there's a change in DynamoDB table rows, it can trigger a Lambda function. We can perform some kind of an operation on top of the data that is coming in, and then probably trigger another data source, or perform whatever logic that is required. Requests from endpoints, like for example, we have HTTP endpoints wherein we can have a REST API or a GraphQL API, wherein when the request comes in, a Lambda function is triggered, and it performs the request and returns it back to the client. Or any changes into other cloud services. As I mentioned, there are a bunch of triggers that is available as a part of Lambda functions, which we'll probably be covering as a part of this series, where we'll be talking about SQS, SNS, S3 trigger that I've talked about. So we will be covering all these things as a part of this series. And those all things will trigger the Lambda functions, and that can in turn trigger other AWS services or update databases and stuff like that. So this is the basic idea of how we will be working with serverless and the serverless applications. Now, what exactly happens behind the scenes, right? So this is something that is really interesting. So there are two things that you will have to understand. One is something called as cold start, and there's something called as warm start. As I have been mentioning, how does Lambda functions work? There is a trigger, the infrastructure is provided, the request is served, and then the infrastructure goes away, correct? Now, this is a pictorial representation of the same to better understand what exactly happens. So, as you can see, there are two parts to it, the left hand side and the right hand side. The left hand side is the cold start. Now, what exactly is a cold start? When a request comes in, there is no infrastructure that is available, right? So AWS has to provide that infrastructure wherein it can run our code and serve the request. So the amount of time it takes for AWS to provision the infrastructure, that is, bringing up that infrastructure, downloading our code into that infrastructure, starting the execution environment, and bootstrapping the runtime together is what is called as a cold start. Basically, this amount of time is not the amount of time that is taken by our code, but rather it is the amount of time it takes for AWS to provision the environment so that our code can run. So that is what is called as a cold start. Now, what is a warm start? A warm start is basically the amount of time it takes for our code to start and perform whatever we want to achieve with our particular code. As you can see, the left hand side of it is the AWS optimization. The right hand side is the optimization that we have to do on our end. Now, what is that optimization that is on our end? Let us first discuss that. One thing to keep in mind is basically when we are building serverless applications, we always have to make sure that we are not consuming every single module that is available over there in the world. We only have to consume or require or import the modules that is required for the performing of our application. That's it. Nothing else has to be used. Now, what is the reason? Why should I not simply import whatever is available? The reason being is this partial cold start and downloading, basically downloading your code, right? Now, what will happen is, as and when there is a request coming in, I will actually, the AWS has to download the code. Now, downloading the code doesn't mean it's only our code that we write, isn't it? It's also the dependencies and modules that we are importing as a part of our application logic. Now, let's take, for example, in the Python world, you're importing the request module, which is used for calling the APIs, third-party HTTP calls. Or in the Node world, you're using Axios for calling REST APIs, right? So these modules are not available by default in the runtime. Even when you are building your application, you would have done a pip install or an npm install of the request or the Axios module, right? Because it's not by default available as a part of the runtime itself. So basically, because it is not available, the infrastructure that AWS brings up, it only gives us the default modules that is coming with the runtime. The Python modules that are available by default is what will be available, and the same with Node or any language for that matter. Any third-party modules that is not available as a part of the default runtime will actually have to be downloaded every single time, and therefore having an impact on the cold starts. Now imagine your code in Python uses request module as well as uses another module. Let's say, for example, image processing, a pillow module, right? So what will happen is, if your Lambda function is only taking care of image compression or thumbnail creation or some kind of an operation on images, then you only import the pillow module. You should not import the request module because some other piece of code requires the request module, right? So what we'll have to do is, the reason being, for this execution of image compression, we are unnecessarily installing the request module onto the infrastructure that is provisioned every single time the request coming in. That is completely unnecessary, right? So that is why it is utmost important to make sure that any application logic we are writing, we make sure that we only import the modules that is required for our application, and as much as possible, try and see if we can get any other module for a lower size if that's possible. So that is one important key thing to keep in mind, because cold start actually impacts the performance of your application, right? Let's say there is an API request that is coming in. Now, the S3 application that we talked about, right? Conversion of a PNG to JPG, or there's some compression and stuff like that. Every time a request is fired, unnecessary modules are getting downloaded onto the infrastructure, therefore increasing the delay. One of the important one of the major reasons a lot of people are still reluctant to move to serverless is the cold start, because people presume that there is going to be a lot of a huge cold start. But one thing that we have to keep in mind when we are migrating is, as I said, only have the required modules that is required for your application, and also make sure that you don't import unnecessary modules as a part of your application. And when it comes to cold starts, please don't assume things, but rather instead what should happen is you just try out a particular Lambda function, create a Lambda function with the modules that you have, and play around and see what is the cold start that is available, that is happening, and then take a call on that. When you're migrating to serverless, just don't presume that there is going to be cold start, and rather just try it out before taking a call on it. So that is what, when it comes to optimization, that is on our end, and AWS constantly takes care of making sure that it increases the performance of the cold starts from their end as well whenever they are provisioning the environment. So I hope this is clear. Now, the next thing that I really want to touch upon is basically from a configuration perspective. When it comes to serverless applications, as I have mentioned earlier, there's nothing much to configure, because we are not really bothered about the infrastructure underlying, right? We are not mentioning that I should provision a VM of this size, of this RAM, and stuff like that. But rather, in the serverless world, we have three things that can be configurable. One is, of course, the runtime. Basically, the Lambda function that you're going to create, which programming language is it going to use? Is it going to be Python, Node.js, Go, Java, .NET? There are a bunch of languages that AWS provides, but that does not stop. If at all a language that you are more proficient in is not available as predefined or pre-available from AWS, you don't have to worry. There's something called as a custom runtime, which you can leverage and write the application logic in your own programming language, and then upload it to AWS, and you can still run it using the custom runtime. So runtime is one of the configurable things. The second thing is basically the RAM, or rather memory. So as of today, memory is configurable from a range of 128 MB to all the way to 3 GB, or if I'm not wrong, in the recent reinvent, they have extended all the way to 10 GB. Uh, it gives us the capability to play around with the memory. So memory doesn't really translate to RAM that is provided underneath, but it is a combination of the power of the machine that is underlying as a part of provisioning of the infrastructure. So as and when we, let's say, for example, you have a particular application that is, compute intensive, then we would probably want to, provision a larger RAM configuration, and therefore give the infrastructure that can be that is sufficient enough to perform that particular operation. Yeah, 10 GB is the maximum memory that can be provisioned for the Lambda functions. Now, there's one thing that we will have to touch upon here is the costing factor, right? The costing, as I said, is pay as you go, but how does it AWS compute that, or calculate that rather? Is basically, first thing, is it is a combination of the amount of time your code takes to run. Now, let's say, for example, a piece of Python code that you have written is taking 500 milliseconds to execute. So then we are charged for that 500 milliseconds. And along with that, we are also charged for the memory because AWS is provisioning that kind of equivalent infrastructure behind the scenes, right? So we will have to, although it is event driven, that means on demand basis, but because it is provisioning the same, we will have to pay for that particular 500 milliseconds amount of time. And so it's a combination of these two, and of course the number of requests that is coming in. Now, one thing to make sure that you guys are experimenting is basically the memory allocation that I have talked about. It is always advisable to make sure that you play around with that memory because it starts all the way from 128 MB to 10 GB. It's not always good to just go ahead and start with 10 GB because that's the most powerful memory that is possible, and I want to make sure that the infrastructure that is provisioned is the most powerful one. That's probably not a compute intensive code that you have written for 10 GB memory or memory intensive infrastructure to be provided, right? So it's always advisable to play around with that memory. Just try out different combinations of a memory that is possible and make sure you achieve at an optimum memory configuration to make sure that you are both leveraging the cost factor because we are charged for the memory that we are allocating along with the time that it takes. For example, you have a very small memory and you have a compute intensive function, then it doesn't really make sense, right? Because it's going to take a lot of time. It impacts both the user experience as well as from a costing perspective as well. So it's always important to make sure that the memory is something that is always tweaked about, and you are playing around with it. So these are the various, just the three configurable things that we have from a Lambda function. Therefore, taking a lot of difficulty from from a developer's perspective. Therefore, we only concentrate on writing the business logic and nothing else or nothing more. So these are the few use cases, just to mention a few, that we can leverage serverless for. We can build web applications, like a few examples that we have already talked about. That is basically, the ticketing platform, the image conversion and stuff like that. Chatbots is another really interesting use case, wherein because it's completely event driven, right? It's not like everybody's chatting all the time. So as and when there are messages coming in, the same gets delivered to the other person. Now, even if you guys have used AWS Lex, which is basically the chatbot service from AWS, it very nicely integrates with the Lambda functions and helps in performing the NLP, NLU, and all sorts of things that Lex takes care, and business logic that is taken care by the Lambda functions. It's not just chatbots; even Alexa skills that we have are mostly backed by Lambda functions, because again, that is very event driven, right? And it's not like someone is going to constantly keep using that skill. So in such scenarios, serverless becomes a very strong use case wherein we can leverage all the scale and costing factors. Data processing is another beautiful use case wherein we can excuse me, wherein the data, the DynamoDB example that I've talked about, right? As and when there are there is data that is pumped into or inserted into DynamoDB, a Lambda function can be triggered, which can probably perform some kind of a processing like analytics and stuff like that, and keep reports and stuff like that ready, because as and when there's a request for a report that comes in, we have pre-computed reports that can be served as is, which is again event-driven, one kind of an application. And then autonomous IT, there is a lot of cron jobs and a lot of things that can be done behind the scenes, which can leverage a serverless, because they are not something that needs to run 24/7. right? It's all on a request basis or on demand basis, and the same thing to do with backend as a service as well. So these are a few of the use cases that AWS can leverage, and we can use the same. Now, a lot of people, who have worked with Lambda functions assume or presume rather that, Lambda is the only serverless service that is available on AWS Cloud, but that's not true. Lambda is one of the compute service which is serverless. We also have AWS Fargate, which is a serverless containers service that is available from a compute umbrella. We have Lambda functions as well as Fargate. Then application integration. We have a bunch of services which are serverless that can help us integrating various components of our application or various Lambda functions or various services that is available on the cloud. A few of them are mentioned here. One is Event Bridge. Now, this Event Bridge will help us, as the name mentions, it's an event bridge between various Lambda functions, between various microservices that is possible. Then we have step functions. Step functions is basically a state machine which is helpful, which is useful in maintaining a state. Again, one thing that I actually forgot to mention about Lambda functions and serverless is basically serverless is meant to be stateless, which means that there is no context that is preserved between executions, between one request and another. And it has, I mean, again, it is actually a few things are maintained between two invocations if they are using the same underlying infrastructure. I'm just not going to get into the details right now, but we have to build the application in such a manner that there is no state that is maintained between two different requests, and it is always stateless. Now, it is not possible all the time to achieve this, right? Because a lot of times our application may require state to be persisted between two different operations, right? In such cases is where the AWS step functions come into picture. Now, as you can see the icon there, it's sort of a flow chart which will help in orchestrating various Lambda functions. Now, let's say, for example, as I've mentioned, the movie ticketing platform that we talked about, right? Now, there are a bunch of microservices that is possible over there, right? One thing is the payments, a payment microservice, which basically talks about, integrates with a payment gateway and makes sure that the payment transaction is successful and all sorts of things. That is one microservice, one flow. Then we have the other flow is to make sure that a particular ticket is generated for that particular user who's booked for the movie, and make sure that is one step. The next step is making sure that the same is notified to the end user in terms of an email or a WhatsApp message and stuff like that. So there are a bunch of things, and all of this is a part of a single flow, right, which is purchasing a ticket. Now here we cannot really maintain a state between different Lambda functions, but rather you can use a step function not only to maintain a state, but rather utilize it to orchestrate different Lambda functions to make sure that our work is done. Again, when it comes to step functions, there is one particular demo that we will be doing, which clearly explains it to you guys about what are the various features, advantages that AWS step functions bring into the table as a part of this series. And then the next one is the SQS service. It is a simple queuing service which helps us, basically you put a message in the queue, like any queuing service. You put a message in the queue, and then you can have a Lambda function as a trigger. So as and when there are messages put in the queue, we have a Lambda function that gets triggered, performs some operation, and probably puts the message back into the queue, or a bunch of things that can be possible, that can be done. That is the SQS. The next one, we have the SNS, which is basically a simple notification service, which is more like, you can send the notifications to users. We can have the PubSub model where you can have a set of users who are subscribed to a particular topic, and we publish a message to a topic, and then that message is sent to all the subscribers of that particular topic. You can send an email and all sorts of things using SNS. Then we have the Amazon API Gateway, which is basically the API service from AWS that helps us creating in REST APIs, HTTP APIs or WebSocket APIs, and that can be configured or integrated with a Lambda function to that can be called by the clients. Another serverless service that is up on the rise and increasing adoption is basically the AWS AppSync. The AWS AppSync is a GraphQL service where gives us the capability to create GraphQL APIs that can be directly integrated to a DynamoDB table or an RDS instance, Aurora serverless, and I mean I'll come to all those services as well, and also integrate to a Lambda function which can perform some business logic based on the request that is coming in. Then we have the data source. These are the various serverless data stores that is available as of today. One is S3, and most of the people, I'm pretty sure, have used S3 in one way or the other, and it is one of the most reliable cloud services across clouds, and that is a serverless data store. Then we have DynamoDB. So DynamoDB is the NoSQL database key value store where we can store data. Again, with DynamoDB, again, there is one demo as a part of this series where we will be leveraging DynamoDB as our data store and store information. The beauty of DynamoDB is, of course, it's NoSQL. Apart from that, is how it performs under scale. So DynamoDB is a service that has been used very extensively by AWS itself and Amazon itself for various services, and it is tested on prod to the highest scale. If you guys are interested, you guys should surely take a look at the various success stories of DynamoDB and how amazingly it works, especially when there is scale. Unlike a lot of other databases, wherein there's a lot of requests coming in and then the performance goes down, DynamoDB actually performs better when there is scale because of the way the sharding and the way it is stored, the data is stored. Then comes in the Amazon Aurora Serverless. So Aurora Serverless, again, for applications that are not, that cannot be made into NoSQL, which is DynamoDB, but rather want to leverage the features and capabilities of serverless, we can go to the Amazon Aurora Serverless, which is basically a serverless mode of a MySQL or a Postgres instance, wherein we don't really have to bother about the underlying infrastructure, and all we have to worry about is the configuration of the ACUs, which is the Aurora capacity units. So as and when requests are coming in, the database scales up and down as and when there is a request coming in, like how serverless has to be. In the recent reInvent, Aurora Serverless V2 was launched, which is still under preview, which brings in a lot more capabilities than what we have as a part of the Aurora Serverless V1, which is generally available as of today. If you guys want to leverage the capabilities of serverless and not really bother about the scale, then you guys should really look into Aurora Serverless, given that the connection management and connection pooling, all those things are taken away from us, and Aurora Serverless takes care of the same. The next one is the Amazon RDS proxy. Again, for people who have already been using AWS RDS as their database, but rather want to leverage the capabilities of serverless in terms of, let's say, for example, let's consider this architecture. We have API gateway, we have a Lambda function, and then we have RDS as our database. Now, as we have already seen here, we have API gateway and Lambda function that can scale to almost infinite as and when there are requests coming in. But can your RDS instance also scale? Maybe not, because it is limited to the instance size that you have provisioned. Although, of course, you can have auto scaling and all those things that is possible, but then it cannot scale as beautifully, as magically as Lambda functions and API gateway, right? So what happens is your RDS instance sort of becomes a bottleneck when it comes to scale and performance, right? So that is when AWS came up with the service called as Amazon RDS proxy. So instead of directly from the Lambda function connecting or talking to the database, that is RDS instance, we rather connect to RDS proxy, which takes care of the connection management and connection pooling for us. Therefore, making sure that the RDS instance is not the bottleneck anymore. And just like the other services, it can also scale up and down and doesn't necessarily have an impact on our application when it comes to scale and performance. So these are the various AWS services that are serverless, which again a lot of people do not talk about or leverage. But as a part of this particular series of sessions, we will be talking about, of course, Lambda functions, step functions, SQS, SNS, API gateway, DynamoDB, and probably S3 as well. So these are the various services that we'll be talking about as a part of this series. And that's pretty much from me for this session. Thank you so much for attending, and I hope it was an informative session in terms of the basics and fundamentals of serverless. We got a basic understanding of how Lambda functions work, and what are the various triggers, and what are the various various services that can be leveraged as a part of building serverless applications. So thank you so much for joining, and we will have a few more sessions when with the various services that I have mentioned.